speaker. Sham has a very eclectic mind, and to illustrate that, I'll mention that he got his PhD in physics from his bachelor's in physics from Caltech, and was PhD in neuroscience from Gatsby. And then he's moved around to many departments. He sampled a lot, and he's worked on a lot of different things. So, and you see that also today. So he's really in the field of these types of problems.
Thanks, Sanjeev, for the introduction. And thanks for Alistair and Simons for keeping the show running, and Shanjoy for setting up this great semester. And of course, Sanjeev for really taking the lead on this workshop. He's the one to thank for it. Okay, so today I'll be talking about representation learning in two different domains. And many of us believe representation learning is important for making progress and achieving state-of-the-art. And rather than looking at this problem in a vacuum, it might help to look at some of the specific challenges that come up in different domains, what are the commonalities, differences, and how to get and how to really advance state-of-the-art. So two domains I'll be looking at today are control and robotics. And in the last maybe 2 years, there's been a lot of impressive advances due to a bunch of deep learning methods in controls. And one question is just, what are the representations being learned? What are the questions here? And recently, in the last year, I've been looking at questions in music. We released this data set called MusicNet, which was, I'll discuss this later, but it's a very large label data set. And music is interesting because, I think it shares commonalities and differences to domains where we've studied quite a lot. So at the low level, I think there's some similarities to vision because there's a lot of kind of signal processing aspects. And I think very quickly, there's commonalities to language when we start thinking about composition. And it'll kind of blend both of these two ideas. Okay, so let's start with control problems. Okay, so in the last 2 years, there's been this benchmark of control tasks in RL Gym. This is this physics-based simulator that Emmo Todorov came up with. It's a really nice simulator because you can design the control systems, test things out, and transfer to real robotics. And it's very, very effective. And these tasks were the swimmer task, which is you have this object here, and you want it to move like a snake all the way up to this ant. It's just four-legged walker, and you want it to run around. There's various cost functions that come up with. Typically, think about it as you want these things to move, stay upright, and do it fast. Okay, so they're all pre-specified in the simulator. And basically, you'll have a control. It takes as input some states, and it'll output an action, and this thing will move around or fall over. Okay.
Do these transfer well to robots or something?
The feeling is, yeah, they actually, in fact, sometimes for planning in robotics, they actually use the simulator internally to do the planning. So I'll come back to this simulator, yes. So the simulator is really great, and Emmo is a real roboticist, and there's questions of robustness, which is a very interesting issue because you might simulate something very, very well in one specific setting, and it might not transfer because the real world there's perturbations. But as of now, I think roboticists really do utilize the simulator, and it's actually used by roboticists as well to design things. Now, there's a question of whether or not these tasks are good, and I'll come back to that. But it's definitely one which has been studied quite a lot among some deep learning researchers and roboticists. Okay, so these are the tasks that we're going to look at, this sort of swimmer, hopper, walker, and cheetah. Why don't I just quickly review sort of RL and some gradient-based methods. So questions about the tasks at all? I mean, I think it's pretty explanatory. I'll show you some videos of these things working later on. Okay, so let's just quickly review reinforcement learning. I think there's a review talk on this before. But, Markov, okay, I'm just going to review RL in the context of Markov decision processes. But we have sort of states, actions. You take an action in a certain state, you move, you get some reward based on the state you're in, and you move based on the underlying dynamics of the world. And your goal is to find some policy which maximizes some notion of a long-term future reward under some starting state distribution. Okay, so that's just RL. Some cases we know the model. Some cases we have a simulator. And And that's the objective function. And obviously, if the number of states are small, you can solve problems like this with dynamic programming if you know the model. Okay, so that's Markov decision process in a nutshell. One way in which people attack these problems is through gradient-based methods. So these are, you have some parametric policy, which means at every state it specifies a distribution over actions you're going to take. And you can compute the gradient of the reward function with respect to your policy parameters. And it has some functional form which you can derive. And the key point of this functional form is you can obtain unbiased estimates of the gradient with Monte Carlo samples. Okay, because you can definitely compute the gradients of your policy with respect to the parameters because you know your policy. And now you just have to weight them not by your immediate reward, like in supervised learning. You kind of have to weight them based on the rewards you see along a trajectory. But you can just work out the math, and you can take a derivative, and you can get samples. And the naive implementation of this, which is called reinforce, this is like a vanilla gradient descent algorithm where you update your parameters based on some unbiased estimates of the gradients. It doesn't work all that well. And there's typically like variance reduction techniques that are needed to get this to work. But this is kind of one default model in which you attack these problems if you just have a policy. You just have a policy parameterization. Okay, so questions about just vanilla policy gradients? The thing that people tend to do when they're using these policy gradient methods is they tend to use basically like a certain preconditioner that, anytime you have some optimization function, if you have some structure in it, preconditioning can often help. And in these settings, somehow because you're parameterizing a probability distribution, it makes sense to take into account the fact that you have a mapping from your parameters to a probability distribution, and this probability distribution takes you to reward. So basically, what's often done is you precondition with something like a Fisher information metric based on this distribution. It's something that, it's funny because I did this paper back when I was in graduate school, and it's one of these papers that from a theoretical mindset, it's hard to prove it's any better, but back then, I was like, who cares? Geometrically, it looks interesting. I tossed it out there, and it seems to be the default thing that's used. And you can think of this as just some poor man's Gauss-Newton sort of method, where you're just trying to do some preconditioning, but it really does help in practice that most of the practical variants are some variant of this gradient descent with this preconditioner. So that's sort of the review that, look, one way we're going to tackle these problems is come up with a parametric model and optimize it with some local search technique. And in this particular case, we'll look at the natural policy gradient, because that's actually what's used in practice. Okay, or a variant of this. Okay, so coming back to partly Sanjeev's question, so there's sort of two state-of-the-art approaches on these gym tasks. One is these trajectory optimization methods, really due to M.O. Todorov, which is if you have the model, what you're going to do is in each state is you're going to roll out, sort of do Monte Carlo rollouts and choose the best action based on your rollouts. So this is something that when you're actually acting in the world at test time, you're still going to be doing these rollouts. Okay. So this is at test time, you still need the model, and you're still going to do the rollouts. So it's a little more costly. It really depends on the task. It can be very costly to somewhat costly, because actually at test time, you're doing rollouts. Okay, another approach, which was surprising for a variety of reasons, is just directly optimizing the policy. And this was due to Sham et al. And Sergey, is they provided some results that were basically model-free methods, that they trained these things with policy gradients with various neural network architectures. And they were model-free in the sense that even though they were using the simulator, they didn't actually need to know the model. They could train it just by acting in the world, because these are Monte Carlo estimates. So you can just sort of take your policy, act in the world. You're going to get samples. and you could pretend like you were just getting these samples as if you were acting in the world. Whereas these rollout methods, you actually need to take sort of multiple samples from the same state. So these you really are relying on having the model. These model-free based methods, you can optimize just by acting in the world. So you need so that means you can actually just simulate trajectories. And what's nice is they give you compact policies where you don't actually have to do the rollouts at test time. So once you've learned, you have a policy and you can just deploy it. Whereas the top ones, you need to actually do the rollout. So I think what's surprising is you really could get these model-free methods to work, and you could just have a compact policy. Yep?
Yeah, but the sample complexity of this is very high, and so it only works if you have a simulator that can run faster than real time.
So I agree with that, and I think that's one of the open questions. So, but at deployment time, you don't need the simulator. So that's what's nice. Whereas this one, you actually need the simulator at test time. Right. So yeah, I'll come back to the open questions. That I certainly believe that variance reduction is one of the critical issues for these model-free approaches, because the policy gradients have high variance. Okay. But I would say that's an open question. So the two things that went into the sauce here was the optimization. They used this trust region method. It's very closely related to the natural policy gradient and the various deep architectures. And we got interested trying to understand what's the notion of representations being learned. Okay, so those are the two state-of-the-art approaches. And we were really interested in just trying to take this and move to harder robotics tasks that they couldn't address. And basically, what Jan's pointing out is the simulation, these model-free based approaches really do suffer from variance methods. And if we wanted to get this to work on very, harder humanoid walking tasks, it was very likely we'd have to address these. So, but again, it's been a while since I thought about RL, and Emma was an expert, so we kind of started from scratch, and we wanted to understand what's the simplest things we need to get these things to work out. So optimization, we just stuck with the natural gradient method because vanilla gradient method doesn't work so well. Most of the variants were just variants of some kind of preconditioned method. These problems, the state dimension you have is typically maybe about 10 to 30 dimensions. So they're typically like center of mass and relative joint angles for these objects. And then there's a question of how should we parameterize our policy to solve these problems? Okay, so what's the first thing you might want to try is let's just try a linear policy. Okay, so here I'm going to show you one of these network policies. And the other one is going to be a policy that we learned with a linear policy. And by a linear policy, I mean the control action. So the action is going to be the forces. Maybe there's like 2 or 3 actions for this controller, which is going to be the forces applied to a joint angle. And one of these is a straight up linear policy. So it's linear in these 10 dimensions. And the other is a neural network policy. And we were kind of shocked once I did a little debugging. It seems pretty good. Okay, so.
Question?
Yep.
So linear, you mean literally linear?
I mean literally linear. We've got I mean linear in these relative, like the simulator, there's sort of natural state space. There's these joint angles and center of mass, and we have a force. And the policy is literally linear in these like 10 to 30 parameters. Okay, and it works fine, and it was a little surprising because even Emma, who sort of wrote this simulator, was like, wow, like linear actually is fine for this. And so that's linear. This is this fully interconnected neural network. It definitely suggests these problems aren't as hard as people thought, at least in terms of the representation needed to solve them. So
you're using the natural gradient method also
yeah, to train. Well, this one was their method, but we trained it ourselves without it. It's not an optimization. issue that TRP, or like in the paper, it's basically the same. There's like minor differences, but it's not an optimization issue. I mean, ideally, you would like to somehow decouple the studies where you have optimization methods and you have representation methods, but ultimately they're tied together because we don't have sort of closed form solutions to for MDPs. So they are coupled together a little, but it's not an issue for these tasks. Okay, so that's linear, at least for this hopper. Yep.
Use the same state for the linear and the neural network?
Yeah. Yeah. So this is like straight up. So the neural network gets the same thing and feeds it through multiple layers, and they're really identical in terms of how they look. And to be going back to Sanjeev's policy, so the linear policy parameter, so S of t is our state vector. We're just learning a matrix that maps it to the actions. We need to make it stochastic because to take these gradients, you need a stochastic policy. So we have some covariance matrix, which is diagonal. That's how they train even the neural network controllers. They have some function approximator, and then they have some diagonal covariance matrix to make it stochastic. Okay, and then you just take your policy gradients. And then we also decided to beef things up with one of these radio basis function kernels, because this is sort of my straw man stupid thing to try. These are I never actually implement it with the radio basis function kernels. I use these sort of random Fourier features. So Ben and Ali a long time ago argued that these are good approximators to RBFs, basically just by Fourier's theorem. This is sort of a poor man's way to approximate a radio basis function. So the way the other thing we did was you just cook up a whole bunch of random features based on Fourier transforms, and then optimize them still with a linear policy. We're not optimizing these weights. So this is just to enrich the space to make it a little beefier, but it's still in the what I would argue is simple, that my straw man approach is just linear and some kind of well-behaved low-degree polynomial, and this is sort of a random way to learn something in that space. Okay, so but linear is the one that it's just straight up linear in the given state variables. Okay, so now let's look at the performance curves for these 5 tasks. So what I'm looking at here, so this green line is the published neural network architecture results. And the red line is linear, so this is iteration, and this is the performance, and the blue is the RBF. So linear works fine on all of these. You see this cheetah, linear is a bit worse than the neural network, which is a bit worse than the RBF kernel, but still let's come back to the cheetah, but still like you're getting some performance. But all of them, I'd say, are competitive. And in terms of train time, the training time is basically straight up proportional to the number of parameters in the model. So linear, we've got about 100 parameters, because typically there's, I think, between 3 to 5 actions in these tasks. So that weight matrix is about 100 parameters in these tasks. So the RBF, there's like 2,500 parameters. Some of these deep learning architectures are 10,000. So it's like, I don't know, like 10 to 15 minutes to train one of the linear things, maybe 5 to 10 hours for some of these neural network ones. The RBFs are somewhere in between. Note that we're not saying the linear is the best thing, the best thing to do for much harder tasks, but it is, at least this set of benchmarks is not resolving some of the representational questions that we might be interested in. Yep.
Is there any difference or issue at all of stability between all of the 3 methods, or do they?
Great question. Let me come back to that. This is really, it's a great question because, the hope is, we do want to get good working robotic systems, and stability is really one of the questions we care about, so I'll come back to that. And we want ways to make these tasks harder so we can really study the representational questions, because I firmly don't believe you can just be linear in the state space for really hard tasks. But the fact that you can do that here suggests that we aren't going to address the representational questions with these benchmarks. Peter?
The trained neural nets, are they computing policies that are substantially different from the linear policies?
I mean, they look the same.
They compute.
I think they look the same, and they're getting the same value function. I mean, this is the performance. It's hard to, we didn't explicitly look at the. we didn't look at the KL difference, but at the end of the day, I think there's kind of one sort of controller that works well. But let me come back to the perturbation one and argue that they're similar in a sense. So the other thing I want to emphasize is that while we cook up these performance metrics, to some extent, we don't really believe that these performance numbers are what we're interested in these robotics tests. They're kind of a surrogate for getting the system to do what we want. But I'd argue that this difference, I'd say the hard part is getting these things off the ground. And subjectively, once you have it off the ground, you've basically got it in a stable state around the right answer, and you can tweak it from there. So to emphasize that, I'll say let's just look at the difference between the biggest gap in performance between linear and the RBF controller. So linear is down here. It looks like it's a bit worse than this RBF and this neural net's in between. So let's just look at the controllers. So now guess again. One of them is the RBF controller, and one of them is the linear controller. This one you could probably guess the difference. Any guesses? RBF is the bottom. It's a bit faster. But by any account, if you see this and the linear is working, you can beef it up because you've really got this thing to work. It's not just falling over randomly.
A question is a little surprising. As we know, a kernel with random feature mapping is actually a two-layer neural network. The hidden layer is randomly initialized, and the full connected layer is fine-tuned, and the activation function is cosine. If you do the neural network with random initialization, it should be at least as good as the kernel method. So I'm surprised why it's worse in some cases.
Okay, it should be as good if everything was convex in the world, and the point is the world isn't convex, and we have to deal with real training. We have to deal with the real training issues. So this isn't an issue that we have tanh versus the sigmoid. It's just, look, you train this in some way, and it's going to be a function of your training algorithm. And note that for these tasks, like actually just clamping the first, for the neural net, we tried this as well with sigmoids, that you could just clamp the first layer to be random and it works fine. But this isn't too surprising that linear works well. Like once you see linear works well, it's kind of obvious that just bolting on a little extra stuff is going to make it work well. But okay, so the main thing I want to emphasize here is that from the robotics standpoint, linear basically solves the task. And getting it to improve from there isn't really that difficult by just augmenting some nonlinearities. Okay. Now for any questions here? Okay, so now for the right question, which is, look, all of these things work, but we do care about stability, and do these policies behave any differently when it comes to stability? And I think we've established that for trying to look at these harder questions, the way these tasks are set up doesn't cut it. So the first thing we tried is let's just give these robots a big thwack because we've got a simulator. So wouldn't it be fun to just smack it and see what happens? So this, I think this is a linear policy. So now, so the red arrow is we give it a big kick, and then whoa, knock it over, tries to get up, it fails. And this is an issue for all of these tasks and all of the policies. None of them generalize any better when we start thwacking it. So for the snake, you can't thwack it, but we can turn its direction, and somehow it doesn't know how to move. Like it knows how to move forward, and you just rotate it, it stops moving, which is totally bizarre. And the walker, we just knock it over, it's cycling, and it just stands down, and this is a neural network, this is an RBF, these are linear policies. So in terms of the robustness, they're all terrible. And you would like them to be able to get up on their own. And this is partly due to the fact that
you'd have to define a get-up task.
Yeah, but you might hope that so we tried to start it just for getting up, but if we let it run for a while, it typically just forgets how to get up. And but this is an issue that I think people thought these were hard, and for these harder walking tasks, if the carrot is up top and you start on the bottom and you act randomly, you're never going to go up and get the reward signal. So typically they start them upright, so they're in a regime where the gradients are non-zero. But in these tasks, they're simple enough that just some sort of random initializations should at least get them some reward, because they give them a little reward for getting the center of mass up higher. But in the harder tasks, this is an issue. But what Sanjeev is saying is right, that look, if what we care about is this, is getting them up, we need some reward. The way we actually solve this is let's just try to initialize these things in a diverse state distribution. And I'm not convinced this is the right way forward, but we might as well try it out to see if this makes these tasks any harder. We can get more robust controllers, and maybe we can get some intuition between how to enrich our policy space.
Have we tried to smack them only if they don't go fast enough?
That we haven't tried. That could be entertaining. I think in these tasks we could actually get that to work. If it gives them a velocity bump and they can control it, maybe they want the little boost. But we haven't tried that. Okay, so so everything really breaks in the presence of perturbations. The representational advantages don't seem to help at all if we don't couple them with the training.
How about tiny perturbations? There must be a limit. Maybe
there's a limit.
You can compare them with respect to this kind of robustness.
I think in terms of, we can, but I think that the point I want to make here is that the tasks are pretty easy, and we really care about harder tasks. So, right, I don't really care about the differences between these policies at this point, right? We want to make harder tasks, and why are they brittle to perturbations? Well, it's kind of obvious, right? These learn policies are very trajectory centric. They're optimal where they, where they tend to visit. It's a very different issue than in supervised learning, which is like if you're optimal under the distribution, great. In real robotics problems, being optimal where you visit isn't great because the system will be shaken a bit. So, the naive thing is we're just going to use a diverse initial state distribution, see if that works, see if there's differences in these policies, and I think it's an open problem for how to really deal with robustness issues more generally. But once we sort of train with these diverse initial conditions, then linear doesn't solve, then there's a somewhat difference between linear and the RBFs. Like the linear is still somewhat okay, but it's not nearly as good as the RBF in neural networks. But the RBFs, they're hard to beat. So I'm not going to give you show you the performance plots, but RBFs in the paper are pretty much the best here. But still, we can solve all of them, which suggests they're pretty easy. So these things will show you a kick we should see at some point in time. There you go. So you see some of them get hit, but they come over. I think this one will get a large force, and we turn the snake around, and it'll still move forward. Lo and behold, if we rotate it, and the same thing for the hopper. So all of them get solved if you just beef up the RBF a little. And for the most part, the linear isn't all that bad. Like sometimes it won't work, but the fact that linear is still okay is I think it's still a little surprising.
So to get them to sort of be more robust, so you're like kind of starting them at different.
Yeah, I'm just starting them at different configurations in training.
And then just beefing up the RBF is sort of enough.
Not even beefing up, just using the same 2500. Yeah, and same linear, and it's so there's no real augmentation in terms of the network architecture. Just we're retraining under these different distributions, and it seems fine. So the take home is. We're certainly making a lot of progress in robotics. There's a number of issues to address with regards to robustness, representation, and what it means to get to harder tasks. But the current set of benchmarks don't really resolve some of these issues. So I think it's just keep pushing forward, start looking at the harder tasks. I think there's technical challenges, which is how to deal with the variance issues in these policy gradient methods, because we do want methods that when we deploy them, we don't have to do rollouts. So I think that's a very nice question. But we also don't want to pay the high variance at test time. even with a simulator, because it is costly to do these runs, and we're doing them on GPUs. And so a little longer. So that's all I'm going to say robotics. I'll just briefly discuss some of the insights in music and discuss this data set. Are there other questions here? Yep.
To use policy gradient methods, you have to have an estimation of the value function.
Sorry?
You have to have an estimation of the value function.
For
the policy gradient methods.
we get Monte Carlo estimates of it. We aren't estimating the value function in a parametric manner. We're computing estimated values on these trajectories by simulating them. So this is sort of reinforced, and this natural gradient just sort of gives us better mileage on the gradient estimates. Okay, so topic switch. So I try not to make it too complicated, but it's again in this question of we want to learn interesting representations. What are the insights in different domains? So, you know, in many different domains, we know large label data sets are great to have. Music is a domain where it would be nice to also have a lot of label data. It can be hard to get. And by label data, what we might want to know is take a particular piece of music, take a random time, what are the notes and instruments at that given time? Okay, this could be very helpful because if we had this, we could try to take a piece and try to train an algorithm to recognize which notes are being played when and which instruments. Okay, and it's difficult to get labels like this because you can ask a human to label a piece, but then I can give you a piece like this Ravel string quartet. Two violins, a viola, and a cello. I say label this piece. It's going to be, an expert could do it if they slow it down and mark, every 50 milliseconds where things occur, but it's difficult. Yep.
Isn't the score itself a labeled data?
Score is a very crude label data, and you could think of the analog of speech recognition of where you take, you ask people to read essays, and then you have labels, which is, this is what someone said, but what we really want to know is at each time point what is being played. Okay. And that's important. And the same thing with speech recognition. You want to know, when I said the word music, like at which particular time point was the M said, and you want this alignment. And what we did is we actually found a way to align the scores to the music. So to first order, there's a data set which has done this alignment. So we released this data set, we called it MusicNet, inspired by ImageNet, where it's over 30 hours of aligned music, and it's real professionally recorded music. It includes that Ravel piece that's actually aligned on roughly 20 millisecond intervals. So it tells you at each time point what instruments and notes are there. It's again, it's sort of limited to the classical domain, so Baroque to Romantic, 10 instruments, 10 composers. The short answer is, as far as the machine learning standpoint is concerned, you could assume that we've solved the music to score alignment.
What are the labels exactly? It's a set of instruments?
So the labels would be
every 20 milliseconds?
So what you're going to get is you're going to get a time series of pressure, which is sound, and a label would be take any given time point, and it'll tell you the note that's there. Or another way to put it is, let me just show you exactly what the labels look like in the data set. The data set is going to be just a large table. It's going to have a start time and an end time. So this is exactly what's in the data set. So the start is 45.29, that's seconds. The end time is 45.49. The instrument's a violin. The note is G5. The measure is 21. The beat, and it's the note value, 8th note. So it's the interval is where the notes appear, and it's marked for all of these instruments.
But this won't work for jazz where the score is very approximate.
Yeah, so I think it's a great question of how to transfer this. But in a sense, there's two separate issues: how we constructed the data set, and then what do we do with it. So classical music was, we did this by sort of what you suggested, is we took the real recordings, we aligned them to the scores. We took the scores generated, synthesized music, and found some way to align it. But as far as you're concerned, you have a data set of professional recordings that are annotated with a data set that looks like this. Okay, and to show you a demo of what it looks like in pictures is this is the pressure signal. This is, in a sense, the score. These are the durations of the notes. When I hit play, you'll see the alignment, and it'll tell you when notes are on and off. Play here. It's getting brighter when the note starts and ends. Time, so you can see. Hopefully it's clear what's going on here. Okay, so that's a visual way to align things. Yep, Jeff?
Have you tried resynthesizing the music just from the line score that has the temporal nuances of the actual real performance to see whether or not you're capturing something about the score? That would also be a way of verifying that there aren't timing errors in the alignment?
So the way we did check the errors is we just sampled it and explicitly slowed everything down and independently checked for the alignments by slowing things down. So sampling is a good way to check things. And then we had people independently.
You could resynthesize it just from the aligned score.
Yeah, there's a bunch of ways. There's a bunch of ways to do that. We haven't looked at that method, but we did make an attempt to estimate the error rates in the procedures by sort of independently slowing things down and spot check. It's much easier to check how accurate things are, and we're thinking it's like under 4% errors. I'll say, look at the paper for details, but I think there's a strong case to be made that the data set is, it's extremely high quality and it's readily available. So I'm not going to go into the details of that. I just have a couple of minutes and I'll wrap things up. I just want to say the data set's out there. Go to town. This is just a list that, lots of minutes, lots of labels, very diverse set of instruments. It goes up to even a few octets in there, but lots of quartets. And that Ravel one, I believed it was robust because, John, the student on this, I was like, of course this works in piano. And then he showed me the Ravel, that really fast Ravel piece on a 10 millisecond interval. I'm like, okay, let's just make the data set, release it for the public. We got Creative Commons music, so we could release it. It's out there for you to use. We're really hitting the supervised learning questions. So I think the first question obviously is, if we just did a data-driven way, what are the low-level features learned? We'd kind of expect some kind of spectrogrammy features, and lo and behold, that's what we find. But there are definitely sort of training issues. I think the interesting questions start coming in is once we have these low-level features, then my feeling is we need something like a language model for how these things are put together, and we're thinking about this now. I would say at least, just wrapping up, where we're at now is, we've got some low-level features, but I think the right thing to do here is just use spectrograms, and it's arguable in vision too. Probably the right thing to do is just use some Gabor features, which you can handcraft as well. The interesting thing comes up is what do you do with mid-level representations, and that's an exciting question. Representational learning here, I think, should have some interesting analogs from what we've done in other settings. So this is these cool demos from Vision of style transfer, where you take one image, take another, you can put them together by what these con nets have done. So this is, I don't know if people have probably seen this. You take two images and transfer the style. It'd be really interesting to see if we can do analogs of this in music, if we understand the structure of music a little better. There's definitely some musicians that we're collaborating with to understand these issues. There's various kinds of in-painting questions which would be really interesting to play around with in the space of music. So to wrap things up, so at least one direction I've been thinking about, in addition to sort of the mathematical questions we have in optimization and representational learning, we really want to get insights from different domains and get a toolkit that's broadly applicable. There's different challenges in different domains, surprisingly. So for the controls problems, this was joint work with Kendall, a researcher at UW, who's really got some great insights. This was really Arvind's baby. He did fantastic work on these RL problems. Emo is just extraordinary in controls. He sort of built that simulator. On the music side, Zaid is a recent hire in stats. John did phenomenal work in the music domain. We were completely off base when we started the music project. We were like, let's just try to use synthesizers to do everything. It wasn't working. In less than a year, John gave us this data set, and we released it. He's really done fantastic work. And more broadly, there's a lot of exciting questions looking at these representational learning questions in particular domains, and lots of open questions. Thanks.
Time for a question or two. The next speaker can come up and set up. Questions? Yeah.
Yeah, so the low level, it's basically some kind of ConNet RNN for learning these low-level features. For the mid-level, this is a good question of how to tie these things together. And we haven't had much success with RNNs because just the optimization issues don't seem to work out of the box. Like even for these low-level features, they were just optimization issues. I think it's due to the fact that the conditioning in these music problems it's significantly more poorly conditioned because you've got these low frequency filters up to very, very high frequency filters, and I think this just causes a lot of problems in the optimization. So I think some core optimization improvements could help, and how to couple this with a time series model I think is a great open question, and we haven't just the naive things we've tried we haven't been particularly thrilled with. Yeah.
Okay, thanks.